So in our first technical section for the course, we're going to talk about a general overview of the Nexus switches. What are the differences between the platforms and what are the general roles that the boxes play? And then we'll look at how they're going to fit into our specific topology that we're going to be using for class, and what are the type of technologies that we're going to be implementing on the specific boxes. So first and foremost, one of the main links that you guys want to know is going to be the just overall Nexus data center page, which is going to be at cisco.com/go/nexus. And then we're going to be breaking these down into the Nexus switches versus the MDS SAN switches. And then within Nexus, what are the different sub-platforms. Now, when we compare these to the enterprise switches like Catalyst, most of the time we break these down into 3 layers in terms of core, aggregation or distribution, and then the access layer. And now when we look at Nexus, the roles are kind of mixed here because in a lot of designs we don't have a clear separation of the core versus the aggregation, and we run what is known as a collapsed core, or as we'll see once we get into more detail, what is sometimes referred to as a CLOS fabric, or CLOS, which means that we have a spine leaf topology, or basically access layer switches directly attached to the core, which we'll see is the reason why that a lot of these switches are going to be playing dual roles, where the Nexus 9K switches can be both in the core or they can be at the access layer, where the core switches would be the spine switches like the 9500s or the 9336, which is sometimes referred to as the 9500, okay, not the 9300, or the 9336, which is sometimes referred to as the baby spine, which is basically a fixed format or fixed form factor for the core switch. Where then we have the access layer switches. These are going to be the ones that are directly attached to the servers. So it'll start to make more sense once we start to get into the individual technologies. Like we look at how virtual port channel is implemented, or how VXLAN, how ACI is implemented, and then we'll understand why you would use 9K at both the access layer and the core versus using 5K at the access layer and 7K at the core. Depends on what particular specific technology that we are trying to implement. Now, the first of these, which are going to be the Nexus 9Ks, these are both in fixed format and in a modular chassis. Okay, more specifically, modular chassis is going to be the 9500s. So if we go back to that overall page for Nexus, and then we go under 9K for compare models, we have the 9500, which is going to be the modular chassis. Okay, it looks like your classic Nexus 7K, Catalyst 6500, etc., where we have multiple supervisors, we have multiple power supplies, multiple fabric modules, multiple line cards, and so on and so forth. Most of the time, this is going to be the core aggregation switch, where we can see under the line cards we have 100 gig E modules as well as 40 gig E modules. Normally this is going to be for the spine aggregation. Okay, also we'll see that the big major difference here between the Nexus 9K and the other platforms is that this is the only one that supports the application-centric infrastructure, or the ACI, which is going to be our software-defined networking, or our SDN implementation from Cisco's point of view. So in our case, the topology that we're going to be using, the Nexus 9K is going to be running in ACI mode. So we're going to be accessing it from the APIC GUI, the application infrastructure controller. But Nexus 9K can also run in NXOS mode and behave just like a 7K, 5K, 3K, etc., where the syntax is identical between the two platforms. But main difference here being is that Nexus 9K is the only box that can run in ACI mode, and actually this does read correctly. I thought I misread it. All other Nexus platforms support only NXOS mode, where Nexus 9K is the only one that runs in ACI mode in addition to that. But be aware here that these two modes are mutually exclusive. So it runs a separate software image where you have to flash the firmware differently for NXOS than you do for ACI mode. You can think of this as loosely analogous to like a wireless access point, where you can run it in standalone mode, or you can run it by the controller. but they're going to be two different software images if you're running it standalone, like regular iOS, or you're running it through the wireless LAN controller. In our particular case, the equivalent of the wireless LAN controller is going to be the APIC, the Application Policy Infrastructure Controller, or basically it's a dedicated server that from our point of view, we're going to be accessing it from the GUI or accessing it from its APIs. Then the APIC controller is going to be making API calls to the actual physical switches, like the spines and the leafs, and then telling them to do their configuration changes, like to create VLANs, to assign trunks, to do layer 3 routing. And we'll see the main difference in the paradigm shift from our traditional networking versus ACI or versus SDN is that we're going to be managing the network as one entity overall, like basically one giant switch, as opposed to individual separate management access points. So like in your traditional enterprise network, you would have 100 access switches. You'd have to log into 100 different CLIs in order to create VLANs, in order to do trunking, and so on and so forth. But within the scope of ACI, we control everything from the APIC, make our centralized changes there, and then all of those changes are going to be pushed down to the spines and the leaves. But like I mentioned here, specifically within the platform lines, there's going to be two different variations of the Nexus 9Ks. So we have the 9500s, which are going to be the modular chassis, and then we have the 93 and the 9200s, which are going to be the fixed switches. So in our particular case, we're going to be looking at the 40 gig E variations of the 9300s. This is going to be the ACI spine. And then we'll be looking at the 9310 G-base, not 10 G-base T, but the 10 G-base SFP, where these are going to be physically connecting down towards the servers, okay, like our UCS servers, for example. From there, the leaf switches are going to connect to the spines, and then this is going to be used to route the traffic between all of the servers. But we'll see that the key point here is that some of the boxes only run in NXOS mode, which is going to be mainly the 9200s. Okay, you can see here it says standalone NXOS mode only. The 9300 ACI spines are going to be running in ACI mode only, and then some of the boxes can run either or. Okay, so NXOS or ACI, but these are going to be running different software versions, and then you would have to manually switch between the two in order to run one versus the other. So it would be a disruptive upgrade basically to move between the modes for them. Okay, so 9500, this is going to be our redundant box. This is the one typically that you would run in the core. So we have redundant supervisors, redundant line cards, redundant power supplies, etc. Same as like a Nexus 7K or like our traditional Catalyst 6500. Okay, next one we have is going to be the Nexus 7000 or the Nexus 7K. This comes in two different variations, which is the 7000, the original chassis, and then the 7700. Both of these are modular chassis. So we'll talk about this in more detail later once we start to get into the configuration of the Nexus 7K. But there's going to be different line cards that have different software features available to them. And there's a link here that you may want to look at after the class, which is the module comparison matrix, because not all of the different line cards are compatible to run in the same chassis and to run inside the same virtual chassis or the virtual context within the Nexus 7K at the same time. Okay, in our particular case, when we look at the 7K models, and then we look at the supervisors and then look at the line cards, in our particular case, we're going to be using a Nexus 7K with supervisor 2E, which is the current version. You can see for 7700 and Nexus 7K, this is going to be the current processor. And then in terms of the input-output modules or the I/O modules, we're going to be running the third generation cards, which is the F3 cards. And specifically, we're going to be using the 48-port 10 gig card, which is the F3 48 card. And you can see inside the part number, actually, we're going to be using this one here because it's for Nexus 7K. Some of them are for Nexus 7700, some of them are for Nexus 7K. And these are not going to be compatible between the two chassis. So in terms of software configuration, We'll see syntax-wise it's identical between the two boxes, but they're a different physical form factor. They have different power supplies, supervisors, etc. And then, like I mentioned, the current version of that is going to be the 7700 chassis. Now, in terms of the role, one of the key differences between the Nexus 9Ks and the Nexus 7Ks up to this point is that Nexus 7K can be a core LAN switch, but it can also be a core storage switch. Now, I believe that Nexus 9K in the newest software releases is starting to introduce fiber channel over Ethernet support, but it's kind of an afterthought for the platform. It's more designed to be layer 2, layer 3 LAN access, where Nexus 7K is designed to be both Ethernet aggregation all the way from 1 gig access ports up to 100 gig Ethernet for layer 2 and layer 3 LAN switching, but it also supports fiber channel over Ethernet. Now, when we look at this versus the other lower level Nexus platforms like the 5K and the 6K, one of the key differences here is that the Nexus 7K does not support native fiber channel or native FC, which is going to set this apart from the previous multi-layer director switches or the MDSs versus the Nexus 7K. So physically, you'll see that they look pretty close to each other, like the MDS 9700 versus the Nexus 7700. Basically the same chassis that they're running in, but behind the scenes in terms of the line card support and the software support, Nexus 7K does not have any native fiber channel line cards. But like the Nexus 9500, Nexus 7K is going to be a redundant platform, so it supports redundant supervisors, the CPUs, redundant line cards, redundant fabric modules, power supplies, which means that it does support stateful switchover and in-service software upgrades. Okay, these we'll talk about in more detail once we start to get into the specific implementations, but it basically means that if you have a failure of one of the CPUs, it can use the secondary CPU or the backup or the standby supervisor as opposed to just dropping traffic and then basically, not being able to reach whatever resources that it has behind it. Also supports in-service software upgrade or ISSU, which means that you can upgrade the code or you can downgrade the code without having to reboot the box. So you can continue to forward traffic without having to, theoretically, use a maintenance window in order to have an outage. Okay, same as the Nexus 9500s. Okay, the other main platform we're going to look at is the Nexus 5K. We have these grouped in here with the Nexus 6000 as well, which the new Nexus 5600s are actually the Nexus 6K as rebranded as the 5K. So they're basically the same platform. I think the Nexus 6K customers were kind of confused as to where it specifically fit in terms of its role in the network. So it's being rebranded as the 5K, which people are generally more familiar with. But in general, this is going to be typically our access switch or our aggregation switch. And key here is that this is going to be access or aggregation both for LAN switching and for SAN switching. So it supports 1 gig, 40 gig, or 1 gig, 10 gig, 40 gig Ethernet down to the access layer, and also for uplinks. Supports layer 2 switching and layer 3 line rate, which in the previous generations, in version 1, it was a layer 2 only switch. In version 2, the Nexus 5500s, it supported layer 3, but not with the greatest performance. With the current iteration, the Nexus 5600, it does support both layer 2 line rate and layer 3 line rate natively. And one of the big features that we'll see a little bit later, once we start to get into the details here, is the VXLAN, or the Virtual Extensible LAN hardware gateway that does both layer 2 and layer 3 overlay forwarding at line rate. So you can have 10 gig access down to the server, or potentially even 40 gig access down to the server, that you're doing your layer 2 tunneling without having to take an additional hit in performance. Now, one of the key differences here, again, between the Nexus 5K and the 7K, or technically the 6K and the 7K as well, is that the 6K and 5K support not only fiber channel over Ethernet, but they also support native fiber channel. So if we have a native fiber channel attached storage array, then we could plug it into either 6K or 5K, or if we have any end hosts that are running native fiber channel, like 16 gig and native FC, then you can physically plug those in at the access layer. Okay, next one we have is the Nexus 3000. Now, we're not going to be using this in our particular physical topology, but Nexus 3K is going to be pretty similar to the Nexus 5K in terms of its role as a fixed access layer switch. The main difference, though, is that the Nexus 3K is going to be used for programmability, where there's a bunch of APIs that you can access on the box, like you can run bash scripting right on box, or it's also used in low latency environments, specifically when you're dealing with high frequency trading or HFT. So one of the big advantages of the Nexus 3K is that the port-to-port latency, or how much delay there is to move a packet from one interface to another, is very, very minimal as compared to a lot of the other boxes. So this is going to be the competition basically for the Arista switches that are used in financial environments. But from a CLI point of view and an implementation point of view, syntax is going to be the same between the 5K, the 7K, and the 3K. Just typically, this is going to be our access layer switch that's going to be used for low latency. Okay, the fourth platform that we're going to be dealing with within our case is going to be the Nexus 2000s, which is known as the Fabric Extender or the FEX. The difference between this and the other platforms is that it's going to act like a line card of a remote parent switch. So if we think of physically our modular-based chassis like a Catalyst 6509, okay, you have your physical chassis, and then inside of it you have your supervisors. So you have your supervisor that is your primary, you have your supervisor that is the secondary, and then you have your line cards. Okay, like you have a 48 port, 1 gig Ethernet card. But you're physically plugging this into the chassis, so it's a module that you're actually, inserting. And then when it connects to the bandwidth on the backplane, it's connecting to that physically over the bus of the chassis. Like there's no wiring that you do physically. It's going to connect on the actual motherboard, the board of the actual line card. Now, when we compare this to the Fabric Extenders or the Nexus 2Ks, we're taking that connection that would be physically on the backplane of the modular switch, and we're changing this into physical cables, either copper cables like twin-ax, or fiber optic cables, either single mode or multi-mode fiber. And then from a configuration point of view, just like you would do in a modular switch like Catalyst 6509, you configure the switch as a whole. You don't configure the line cards individually. And same is going to be true here from the Nexus 2Ks. So it's going to have a parent switch that's going to be like a 9K, 7K, 5K, etc. We're going to physically wire the Nexus 2K into the parent switch, and then all of the traffic that is going to be going between the hosts is going to go up to the parent switch. Parent switch is going to make its decision, and then it's going to forward the traffic back down. So the Nexus 5K or Nexus 7K, etc., is going to be making that routing decision or making that switching decision on behalf of the remote line card, on behalf of the Fabric Extender. Okay, this is used to implement what we're going to call the end of row design, or EOR. Okay, what this basically means is that when you look at your physical topology in the data center, you have your physical rack enclosure, like your 42U rack. You're going to have your end stations, like your servers that are physically in the rack. You physically wire them to the two, or typically two, but it could be one, fabric extender that's at the top of the rack, okay, or a TOR. And then from the fabric extender, you have cables that are running down to the end of the row, okay, so physically to your aggregation switch or your parent switch that is then controlling the access ports that are going down to all of the servers. Okay, the main idea here is that you're cutting down on the number of cables, but you're minimizing the amount of management points that you need in the network. So you can have a single pair of Nexus 5Ks or 7Ks or 9Ks that is controlling up to 20 fabric extenders, depending on the platform, depending on the version, and then likewise those connecting down to all of the servers, and you have kind of one giant switch that has a single point of management for control of the overall forwarding topology. Okay, so single point of management through the parent switches. There's a question here. So what is the use case for the FEX? The main idea is that you're trying to add additional port density, but you're doing so with cheaper switches than you would like your Nexus 5Ks or your Nexus 9Ks. So you don't want to think of these as separate Ethernet switches on their own. They're essentially line cards of the switch that they're plugged into. So if you were to buy a Nexus 2K and plug it directly into your servers, you're not able to forward any traffic. There's no console connection or there's no CLI access to the Nexus 2K directly. So it's basically a way to extend the modular chassis, but outside of the physical enclosure. So you're extending it with physical cables down to the other end of the room, like down to the end of the row, as opposed to having one giant aggregation switch, which you're running all of your cables from that down directly to the servers. So it's kind of a cable management advantage by using the fabric extenders, but it's also a capex issue, basically how expensive the switches are when you're looking at the per port cost going down to the servers. Now, we'll see once we get to the specific implementation of this, the big shortcoming of using the fabric extenders is that you're starting to oversubscribe the bandwidth access for the servers. So if you have two physical boxes that are both connected to the same fabric extender, you cannot send traffic directly between the servers. You would have to switch the traffic up to the parent switch. The parent switch makes its decision, and then the traffic comes back down, which means depending on how much uplink bandwidth you have from the FEX to the parent, that's going to be the bottleneck in the physical topology. Okay, so what I mean by this is that if we had the fabric extender going down to two servers, let's say server 1 and server 2, and let's say we want to do just a ping between these two boxes. Okay, normally in a regular Ethernet switching environment, you'd have your frame go up to the switch that it's attached to. This box is going to look at the MAC address table. It's going to say, hey, I know that I'm going from server 2 over to server 1, and then I'm going to forward my frame down to the destination. But within the case of the fabric extenders, we'll see that these boxes don't maintain their own MAC address tables. They're going to be relying on the parent switch in order to make that forwarding decision. So in this particular case, you would have to go upstream to whatever the parent switch is. Okay, parent switch being, again, like your 5K or your 7K. The frame goes up, this guy makes the decision, the frame comes back down, and then it can forward on to the destination. So this link here is going to be ultimately the bottleneck of the fabric extender design. So if this is a 40 gig Ethernet port, but you have 48 by 10 gig ports going downstream, you basically have 480 gig down, but you only have 40 gigs up. So you're going to be oversubscribing that in what, a ratio of what, 22 to 1? 22 to 1, is that right? So we'll see that it depends on the physical model that we're looking at. And you can see the link here to what the different extender models are. In our particular configurations, we're going to look at two variations of them, both of them being the 10 gig SFP Plus extenders. One of them is going to be the 2348, which is going to be connected in our particular topology. It's going to be connected physically over to the Nexus 9Ks that are going to be running in ACI mode. And then we have the 2232, which is going to be connected to the Nexus 5600 that is running in regular NXOS mode. So depending on how many uplink interfaces that you have plugged into the parent switch, where the 2300, in this particular one, you can have 6 by 40 gigs, and you have 48 ports of 10 gig downstream. So that means that potentially you can have up to 480 down and then up to 240 up, which would be oversubscription of 2 to 1. Okay, but depending on how many uplinks you're using, like in the case of the 2232, you have 8 by 10 gig uplink and 32 by 10 down. So if everything was fully populated, you'd have a 4 to 1 oversubscription ratio. Okay, one of the other differences is that when you look at the extenders versus the physical, or not the physical, but the other regular parent switches like Nexus 5K or Nexus 9K, is that the buffers of the fabric extenders are generally smaller than the upstream parent switches. So you can run into some throughput issues, or sometimes what's referred to as head-of-line blocking, or HOL blocking, where you have kind of a queuing problem and you don't get as much throughput as you would think to an individual server. Okay, so we'll talk about that in more detail once we get to the specific standards. And like someone mentioned here, the oversubscription ratio, like I mentioned, my basic math is wrong as usual, was 12 to 1 in that particular case. But it's going to depend on how many interfaces you have going downstream and how many interfaces you have going upstream. The reason why is that there's going to be no local switching. So traffic is going to have to go up to whatever that parent switch is, make the decision, turn around and come back down that link before it can go down to whatever the end host is. Okay, the last platform that we're going to be looking at within the Nexus line is going to be the Nexus 1000V or the Nexus 1KV. Okay, Nexus 1000V is going to be a virtual switch or a V switch that is running as a virtual machine on top of a hypervisor. Now, in our particular case, the hypervisor we're going to be using is VMware ESXi, but Nexus 1000V is also supported on Microsoft Hyper-V, and it's also supported on Linux KVM. Basically, what this is going to do for us is give us a CLI interface for the hypervisor's virtual switch. So configurations that we would do on a normal networking box, like an access list or a traffic capture, like a switch port analyzer or quality of service, we can then configure that from our normal Nexus CLI, and Nexus 1000V is then going to make an API call to the underlying virtual switch, like the VMware distributed virtual switch or the like the KVM Open vSwitch, and it's going to be programming the software behind the scenes to make it behave as if it was a regular network device. So key here is that this one is not going to be hardware bound. This is going to be a software switch that is running as a virtual machine on any type of server, whether it's a UCS Blade server, a UCS rack mount server, or a white box server like a Supermicro or Dell, IBM, etc. Basically anything that is going to be running a hypervisor on top of it.